The first thing that we will be talking about is arbitrary value imputation. Previously, we have already talked about, for example, like if I say, uh, I've already previously talked about complete case analysis, in which we remove all the missing data technically. If you want to know more about it, there's a complete live stream about it we have previously made. If you haven't watched it, please watch it. Then we talked about mean and median imputation. So when exactly do we need that? We have already made a video about it, which you can watch it. So our previous live stream was about it, and we talked about that when not to use mean and median imputation, or technically when to use it. And so basically, there are very few cases when you can use this. Otherwise, it is not a good idea to use this. Now we're going to talk about arbitrary value imputation. So when we say arbitrary value, so arbitrary value means if you have missing data and that missing data is missing completely at random, and the amount of missing data is not a lot, let's say less than 5%. In that scenario, what you can do is you can use an arbitrary value imputation, because there is one important thing that you have to do whenever you are doing some mathematical modeling. There is one thing that you have to do, and what that thing is, you need to make sure that your model is capable of handling missing values. So your model should be capable of doing that. If you remove all the missing values, then one thing is going to happen. That means during the testing phase, if your data has missing value, your model do not know how to handle it. Model is gonna go crazy and it's gonna throw out some random numbers or some random result as because of that. So if you introduce some missing values and you highlight them that these are missing, now in case of numerical variables, what you can do is you can introduce an arbitrary value. Whereas in case of categorical variable, you can introduce another category in the data itself and you can name it specifically that this is missing category. You can do that. So for numerical variable, what you can do is you can introduce an arbitrary value, and that when we talk about this arbitrary value, it can be any value. For example, majority of the time, now question usually comes up as one question that which value should I take? Means if I'm taking any arbitrary value, whatever number comes up in my mind, the first thing, should I use that or which number should we use? So I would recommend try using a number which is not frequently used in the data, so that you can tag that particular those missing values as that these are separate values and treat them differently. When the model is being trained, that model is going to treat those values differently. So model is going to learn the data based on that different category. So if you're going to use the mean value or median value, so it just like this one, which means then there is no difference between the two things. So arbitrary value is usually a value which is not repeated as much or which is not easily found in the data. So for example, like if I have an age column, so in the age column I would be putting maybe -1, and we know that anybody cannot be -1 years of age, or I can put 99. So because we know that 99 is a very rare occurrence, because normal age of people does not go to 99 as often. So these numbers would be good numbers, or you can use 999. That number is definitely nobody is getting there. Okay, so which means you can use any of these arbitrary values. That is one strategy. Or similarly, when we talk about categorical variables, you can introduce another category and you can name it missing. For example, you missed all the NaN values, all the NaN values with the string missing, which means it will create another category inside the categorical variable, and we are going to be calling that category as missing category, which means whenever that category comes up in the data, when model is training, model is going to learn all the key bits based on that missingness. So this is very important in that particular scenario. So using an arbitrary value is usually a good idea. So mean median imputation was a bad choice majority of the times. We learned that previously. I'm not gonna go talk about it in detail again. So you can go and watch the previous video that we have made about mean and median imputation. But right now, arbitrary value is comparatively better because this makes our model understand that there is a missing data, and it learns how to treat missing data if there is missing data in the testing scenario. So in this particular scenario, if you fill all the missing values with mean and median imputation or things like that, which means your model is not getting trained on some vague values. Now you are training your model on some vague values, and those vague values won't throw up a garbage result, or your model is not going to throw a garbage result because of that. So this arbitrary value can be used for numerical and categorical, both of them. If I use the arbitrary value word, this would be the word I would use for numerical. For categorical, it's technically introducing a new missing category. So in sklearn, there is a complete missing imputation or missing indicator class. So there is a missing indicator class, which you can use just to fill up all the missing values with the missing indicator, and you will be done. And I will show you that in the next video. Right now, I would be covering just the arbitrary value imputation. And then I'm going to be talking about end of distribution value imputation. And then you would be saying that technically, now question usually comes up with, so for age column, I picked up these numbers because they were easy for me to guess. But what about some variables? I don't know what their distribution is and what would be a good value and what would be not be a good value as an arbitrary value for that numerical feature. In those particular scenarios, what we do is we basically use, we plot the KDE, kernel density estimation, or you can say simply the probability density function of the variable. And then what we do is we basically look at the end of the distribution. So we pick up values which are at the extreme ends. So if you know that if I make a standard normal curve, this standard normal curve usually, so let's say this is my mean value. This is my mean value. If I go one standard deviation on the left side and one standard deviation on the right side, what happens is basically I usually, so if I'm one standard deviation away on both sides, so this is one standard deviation on the right and one standard deviation on the left. So what happened is it covers about 68.26% of the data. So this section covers 68.26% of the data. Then if I go in the second standard deviation, so that means if I go one standard deviation further on the left and one standard deviation further on the right, then my whole distribution from this point till this point, it covers about 95.44% of the data. And when I go the third standard deviation away somewhere here, then I cover about 99% of the data. So which means if we go 3 standard deviations away from the middle on a standard normal distribution, then what happens is basically we technically cover from this point till this point about 99% of all the possible values. And this way, doing this would be a good idea, because now if I take any value on the right hand side of this 99% or the left hand side of this 99%, I'm technically picking out some numbers which are at the end of the distribution. So that number would be a good number to choose for some numerical variables whose numbers are, it's very difficult for you to choose what arbitrary value you should be going with. So what would happen if you pick this particular number over here? It's gonna create a new peak somewhere here. And this new peak, so you can see the original distribution of the complete data set still remained exactly the same, but you added another mode. So this is kind of like a bimodal distribution. But this particular section of the distribution is still giving you exact distribution of the original data. And this is only highlighting the missingness. So you can see over here, there is an advantage. That means you are technically highlighting, telling the data that this section, any value in this particular section is a different value. So treat them differently, and the model will learn all the bits based on that differentiation. So distribution, this distribution and this distribution are different, which means any values belonging to this particular section of the curve would be treated a bit differently, because it would consider them differently. Even though model does not know that it is a missing data, but model only knows that it is a different data distribution. So when it is different, then it's gonna learn all the bits based on that difference in the distribution. Based on that, we can see that this particular technique has few advantages over the mean and median imputation. Or you can say that if we do for example, like mode distribution or most frequent distribution for categorical variable, it would have more advantages over that. Let's quickly talk about what are the pros of this technique. So the one thing is, the first pro is it is easy to implement. And then the second thing is basically it lets the model know that there is missing data. So this is important, because if your model is not capable of handling missing data, then that's an issue. So using this strategy, you are telling your model that there is some missing data. I can also write it does not disturb the distribution of present data, even though it adds on to the distribution, which is the negative part. As you can see that it is adding another peak over here, which is not good, but it is not changing this section of the curve. So that is what I'm writing. So it does not disturb the distribution of present data, even though it adds on to it. I'm gonna talk about the cons of this particular technique. So if I talk about the cons of this particular technique, one important thing, even though it is not disturbing the distribution of the present data, but it is adding on to it. That is not good. So which means it does change the distribution of data. So it does change the distribution of data. So if it is changing the distribution of the data, definitely the variance of the data is going to change. And if variance is going to change, the covariance with all the other variables is going to change as well. So variance will change, covariance is going to change, and because of that, correlation with all the other variables is going to change as well. So which means, yes, it has almost all the same cons as the mean and median value imputation, but still it does better than the mean and median imputation. So if I have a choice between mean and median imputation and arbitrary value or end of distribution value imputation, I would be choosing the arbitrary one or the end of distribution one, because yes, I know that Both of them have almost same kind of cons, but one is training my model or giving my model ability to see or train on the missing data in a way. So which means my model is capable of handling the missing data. If I just remove all the data and I only feed the very clean data to my model is gonna be kind of like trained on very good data. But in the testing phase, if my data is not that clean, then it's gonna start throwing garbage. So we need to keep that in mind. For example, like if you are making a particular application for a customer to use, customer does not know how you clean the data. Customer, for example, if you give them a user interface that, oh, put in the age of the patient, put in the for example, like put in the age of the patient, put in the height of the patient, put in what was the result of the ECG, let's say, put in the result of what was the family history for the patient, whether it was, for example, if the patient is coming for diabetes test or something, or maybe heart disease. Let's take heart disease. So if they're coming for heart disease and they're doing some initial analysis, and we have made or developed an application which can predict heart attack or heart diseases, then I would be asking age, height, ECG, family history. So if my age is not present, if I leave it blank, that means missing value. But I can tell the user that when it is blank. So for example, like I can put that, I don't have to tell it to a user, I can do it manually or I can do it automatically, that whenever the user leaves this blank, make it as a new category as a missing value. Okay, for example, like if we have the gender of the patient, so for example, like if this is left blank, I'm going to create a new category. Instead of calling it male and female, I would be calling it missing. So I'm going to give it another label to it. Similarly, for age column, if it is missing, I would be putting in 99 in place of it. So that, for example, if I don't know the age, for example, a patient comes in and patient is so old that patient don't even remember their age and they don't have any documentation and everything. And you would be saying that, oh, let's put in 99 here. Okay, so for the height, yes, we can measure and we can put in there. And for some example, let's say measuring devices were not working well or something like that, or something is missing, I can replace it with the category missing or an arbitrary value, which means I can do that automatically. The user does not know what to do. So for example, like if I am not doing this, that means then I'm not training my model or my application to fill in blank values. So for example, like if the user if the user this particular value blank or this particular value blank, now my model is going to start throwing errors because my model is not getting complete data. My model is getting nan values, and model does not understand what nan means. Okay, or blank values, model does not know what that means. So this is very important. So that one advantage, basically based on that, if I have a given choice choosing between mean and median imputation or arbitrary or end of distribution value imputation, I would go with arbitrary and end of distribution value imputation. Okay, so this is the theory about these imputations. If anybody has any questions, please feel free to write them in the chat and I would be able to answer. And after that, we're going to move to the coding part. Lavanya, yes, it does change the distribution, but look closely here. So if you see over here, this was the original distribution of the data. Let me highlight it. So this was the original distribution of the data which was present. So what I did is basically, I did not change anything here, but what I did is basically, I added another section all over here. So when I use the end of distribution imputation or arbitrary value imputation, it created another peak of its own, which means this whole distribution. So if my model has a data from within this particular distribution, it will treat it as that data is present, and it's going to train based on that. But when this is happened, model is going to understand that, oh, this is change of distribution, because there are several models which do not care about the distribution of the model. For example, like tree models do not care about the distribution of the data. So which means in those particular models, I would be going about that particular model. So we will cover that in later videos, that which model we should choose in what particular situation and things like that, whether if you have normal distribution or not, whether it is skewed or not, so in what situation you should use what. Okay, so we are going to talk about that later, but right now what I'm saying is you can see the original distribution, this section did not change whatsoever. Previously, when we were doing mean and median imputation, what it was doing is it was kind of like squeezing the overall. So if I was doing median or mean imputation, it was doing something like this. That means the original distribution was getting changed. Here, the given data's distribution is not getting changed, the yellow section, but I'm just adding another separate distribution, you can say, onto it. So if that makes sense, then let's move on to the coding part. So what I'm doing is I'm doing exactly the same stuff that I did in the previous notebook, but I have created another notebook. So I will share the link of this notebook with you. I will put it on my GitHub all over again in the same repository, so you can have access to it. But right now, this is not being shared. This is my first version because I just put it together, and I'm going to be showing you exactly the same thing. So this is the same width datathon data set I'm picking up. So I'm using this train.csv. So you can use it exactly the same way as I showed you previously. For example, like if I show you, so what I'm going to do, I'm going to quickly show you the data. And if you guys haven't given an upvote, please do that. It would be okay. So this is the widgets datathon. What you can do is, if you want to use the data set from it, then go to the code, create a new notebook, and when you create a new notebook, you're gonna end up getting that data loaded into the notebook. So once you do that, for example, like if I create it over here, so this is my new data set. So I just created it right in front of you. And what you can do is you can name it whatever you want, and then it's gonna create this thing. So I have created few. I have written some code here, which I'm gonna use because this is a copy paste of what we did in the last time. So so I'm not writing that again, but if you want, you can check it out when I will upload this notebook. So you can see I'm calling in NumPy, I'm calling in pandas, and I'm calling in the train test split. Because remember, I told you that whatever you are doing, all the analysis and everything, the first thing you should do is split your data. Because you don't want, so you have to assume that in real life, when you are doing a real project, you need to make your model without knowing what your test data is going to look like. So you need to separate your test and train set initially, the very first thing, and then do everything, all the analysis and everything on the train test, and then throw in the test set. This is going to give you a better understanding whether your model is doing really good on unseen data or not. So don't do all the analysis. For example, like if you are doing all the analysis with the test data included in the data, that is not a good thing to do. So split the data first and then do anything else. So that is what we are going to do. So this is this train test split is for. Then I will be using simple imputer here. I don't think I would be using this, but I can use it because simple imputer does allow you to put in some random number. And then column transformer means if you want to apply different strategies to different columns, then you can use column transformer. Matplotlib is what I'm going to use to show you the density plots and everything. And I want to show all the columns and all the rows in my data set, but I don't want it to cut it out. That's why I'm just putting it here. If you don't want it, just get rid of them. Then next thing is this particular line is basically I'm reading the CSV file which is present in my input. So this is my input. Dot dot is my current directory, and then I'm going to the input directory. So there is an input directory, there is an output directory. So input directory, I'm going into that. And then you can see I'm writing the name of the dataset, which datathon 2022. And then inside it, I'm using train.csv. This test.csv I'm not using, sample underscore solution I'm not using. I'm using train.csv. So, and then I'm printing out the head of the data. So quick view of the head of the data. This is just a funky thing that I added. If you don't want it, it's a good practice to add comments in your notebooks, because it's good practice to make your code readable so that people can understand what exactly you are doing. Yes, I'm editing. And then over here you can see I printed the data, and this data set has a lot of variables. For the sake of this particular tutorial, I'm not going to be using all the variables. What I'm going to use is I'm going to pick up some. So let me run this again, because I think it refreshed. So let me run this again. So now let's take a look at the shape of the data. You can see it has 64 columns, a lot of columns. Right now, I don't want to deal with that many columns. I will just pick up some numerical columns out of it. This is the information of the data. So if I had not done display maximum rows, you would see that over here, I would not be able to display all the values here. So for example, like if I restart my kernel and get rid of this line, it's not gonna show me all the numbers. So maybe it's gonna cut off after 20, and then it's gonna show me dot dot dot, and then show me the rest of it. But I want to look at all of them. So this is a common practice, good practice to do, to look at the shape, look at the info. Info tells you how many values are missing. So you can see here none values are missing, no values are missing. Why? Because I can look at the shape. This number and this number are same. So wherever this number is not same, that means that's where the values are missing. Okay, that's one way to do it. And then you can look at the data types, that how many are categorical variables, how many are integers, and how many are floats. And some of them can strike you really well in the beginning that, oh, it should be an object column, but it is integer. Maybe something is wrong. Go and change the category of it. So here it gives you the complete detail, the memory usage and everything. You can look at it. Now let's look at the null values. And I want to find the null values. You can see this particular year build has this many null values. This energy star rating has this many null values. And none of these values. So these values have a lot of null values, 60%, 54%, 55, 54%. So what I'm doing is I'm only picking up max wind speed, so this column, and I'm picking up energy star rating as this column, and then I'm picking up site EUI as my Y. So these are, I'm picking two columns as my X variable and one column as my Y variable, and now I'm doing the split. So I'm doing train test split, and I'm dividing it into 80 and 20%. So 80% training data and 20% testing data. Keep one thing in mind, to keep things simple, I'm not dividing into validation set right now, but if I want to, I can divide this into, for example, like 15% over here, which means then I will have about 85% of the data in training set and 15% in the testing set. Then I will divide my training set all over again into 15% and 70% split. That means then I will have in total of 70% training data, 15% validation data, and 15% testing data. Testing data is something which I will never ever use for validation purposes and everything, because when you reach to hyperparameter tuning and cross validation and everything, all those things, I will only be using my validation data. I will never ever show my test data during that phase. I will only show my test data to see my final result, whether how my model is performing on the unseen data, purely 100% unseen data. So right now I'm keeping things simple and I'm putting it here. So if I run this, so did I run it? If I run this, I got this X and Y. Let's split the data. After splitting the data, let's look at the shape. So you can see I got 60,000 values in the training set and about 15,000 values in the testing set. Now I want to look at the mean only in the train test. I don't care about the test for now because I will do everything in this. So you can see it has this many missing values, it has this many missing values. Now, this is what I did previously, mean, median, and everything. So I want to look at their mean and I want to look at their median and things like that. But here I don't care about it. But if you want, you can take a look at their mean value, median value, which is gonna be changed later. Here, if I don't want this, I can just do. So what I did is basically I'm just copy and pasting all the material that I did in the mean and median imputation of numerical feature, the previous video that we made. Okay, so I'm just copying and pasting from there. So just to be sure. So I just copied this because I don't want this right now. I'm gonna comment it out. So I just commented it out. I'm not running it. So here I can fill the values. So I want to fill my values. So maximum wind speed. Now, what is the value for maximum wind speed in this particular scenario? So can we figure that out? Um, if I want to figure that out, for example, like what would be the value, I can look at different values. For example, like if you go and I can find the max of it, so I can write the description. So let's describe it. So what I'm gonna do is over here, before I do this, I'm gonna write x underscore train dot describe. So you can see when I describe it, I'm going to get something like this. My maximum value in the max wind speed is 23.3. My energy star rating, the maximum value is 100. So, and the minimum value is 0, which means energy star rating is going from 0 to 100. And one thing that I notices here is the 0 value does not make sense because there should be at least non-zero values to all the buildings that we have in this particular data set. If something is 0, that means 0 means missing value. We can change it, but right now that is not our focus of attention. So our focus is kind of like whatever we have missing value, because we have a lot of missing value. So we would just take care of that. We would assume that 0 is a valid value. So similarly, max wind speed, you can see we have 1, 1, 1. So 25 percentile is 1, 50 percentile is 1, 75 percentile is 1, and the max value is 23.3, which means I have a lot of ones here and very few values which are not ones, and some values are here. So I need to take a look at different types of values. We can do that. But here I'm just showing you how to do the imputation. So I'm not going to go in detail of doing the complete analysis. Okay. So what I would be doing is I would be showing you how to implement that arbitrary value imputation. And how to do that is pretty much simple. This is 23.3. What I'm going to do is I will pick a number, maybe 24. So I will go and I will say that I will fill it up here. So this is my X train, and I'm going to create a new column in it. When I say wind underscore, so what value should I take? I would take wind underscore maybe max. Okay, so I would say min underscore max, or maybe I would say wind underscore min. So this is where what I'm going to do is max wind speed, and I'm going to fill in the value of what? I'm going to fill in some random value. So I'm gonna fill in maybe 24 here, and I'm gonna fill in maybe -1 here. So which means I can put both of them here. So I can either do this or I can either do this. Since I'm creating two new columns, so I want to show you what's going to happen for both of them. And I'm going to show you the distribution of both of them. Similarly, with the energy star rating, we are going to pick a value, a minimum value. So I will say max rating, and then I'm going to say min rating. So at the end, instead of writing mean rating or something, what I can do is I can write the maximum value. Since I know that the maximum value is 100, I can go beyond that. I can put in 999. And then the minimum value, I know that it is 0, but I can go negative as well. So I can put maybe -1. So when I run this, it's going to be something like this. Let's look at a sample of this. So you can see that wind max, this is 1. So over here it was 9, but I replaced it with 24. Over here it was 9, I replaced it with 24. That was when I replaced it with the maximum value. But over here, I'm replacing it with the minimum. So technically over here, what I'm doing is I'm doing end of distribution or arbitrary value distribution imputation automatically. So, and similarly with the max rating, you can see here it was missing. I replaced it with 999 when it was max. When it was min, I replaced it with -1. So you can see that. Now what we can do is we can look at the variance of these variables. So since I changed the name, let me grab their names and let me find the variance. So since I said that the variance is going to change, let's see if the variance is going to change or not. You can see the variance did change. When I replaced the value with the maximum, my variance went up, and when I replaced it with the minimum, my variance went down. So variance did change over here for my max wind speed column. Similarly, for energy star rating column, the same thing is gonna happen. Let's copy the max rating. So I'm gonna put in max rating and then min rating. So let's print it. You can see the original one was a 21 and it went way above that. And then it went still above, but that is what I'm getting. So this is not mean. So since let's copy the names correctly so that everybody can follow it. Similarly with max. So you can see that. Okay. Now, if I want to plot, I can plot it. So I can plot, for example, like maybe these three together. Let's see how the distribution of all these three look like. So if I put it here, and then, so this particular code I'm using from the previous notebooks. Okay. Okay. So now let's plot it. Let's see what happens. You can see that what is happening over here. Maximum wind speed. The blue one is the original one. The green one is the minimum. You can see it has this blue one already, this green part over here, but it made this jump as well. So it created another one. The rest of the distribution remained same, but what we ended up doing is we basically added another mode to it. Same thing with the red part. You can see that the green part, the red part is just below the green part, which means its shape is very similar, but there is a big jump on this particular end. So I introduced. So these are the things that we need to be careful of. Since there were a lot of values missing, remember the first condition that I told you that the value should be less than 5% missing. But over here, when what I was showing you, the values were missing. For example, like for maximum wind speed, it was 54% of the values missing. That's why it changed the overall distribution as well. So similarly with energy star rating, about 35% values were missing. That means that's why it changed the overall distribution. And that is why it is not a good idea to use these strategies or these imputation techniques when data is missing more than 5%. So 5% number is not a hard and fast rule. It is just a number that usually is acceptable in a lot of situations. For example, like if you have been using p values or alpha values or something, you know that 5% is usually in somehow 0.05 or 5% of the data. If 95% of the data is good, 5% or error is less than 5% or something. So 5% is kind of like a common number. So you can see that it does change, which means should I apply these techniques over here? I don't think so. So which means if I cannot apply this, if I cannot apply mean median imputation, if I cannot do the complete case analysis here, what should I do? So this is where I'm going to cover up our next section. So technically, so far, what I have done is means I have completed a complete case analysis. I have completed the mean and median imputation. I have also completed the arbitrary and end of distribution value imputation. Next thing I'm going to talk about in our next session is I will talk about how to kind of like do all of this automatically. Means I want to test this mean, median, and this value imputation, and I want to test it out automatically. Which strategy would give me best result? Instead of trying all of them one by one, it's a lot of time, right? We should be able to do it quickly. So I would show you how to do it automatically using grid search CV. So I'm going to show you that. And in our next video, I will talk about how to use random value imputation. When I say random value imputation, it sounds like, oh, shouldn't it be just the same thing as arbitrary? And no, I will talk about in next session what is random value imputation. Random value imputation means something like this. So for example, like if you have a data set and if you have, let's say, age column and if you have height column, so you have some data set here. So let's say this value is given this. So let's say this is present, this is present, this is not present, this is present, this is present. So this is where the missingness is. This is missing value. Now, when I say random, what I'm going to do is all the values which are present, 1, 2, 3, 4, I'm going to pick a random number, random value out of the present value and fill this one. Instead of using mean or median or arbitrary values, I'm going to pick a random value from the given distribution of the data and I'm going to fill all the missing values with it. This way, this is the best strategy out of all of them. I'm going to tell you that random value distribution is the best of all of them. And it is also easy to implement because yes, it has few extra steps because sklearn does not provide you, pandas does not provide you one single go, just use fill NA or just use simple imputer to do that. But you have to do some steps. You need to do some masking first. So first you need to make a mask. You need to make a column where you have removed all the missing values so that you can sample from that particular given data and then replace all the missing values in the other one. So yes, it has multiple steps. You need to create a mask and then fill in the missing values. So it has few steps. I'm going to show you next time, and you're going to see that this random value imputation out of these would be the best one because all of these are univariate. So when I say or when I use the word univariate means when I do not care about any other variables influence while filling in the missing data. So if I'm doing that, so the best strategy usually is the multivariate strategies, which I will cover. So there are a lot of them. I'm going to cover KNN and iterative imputation. So these would be in our future videos, but our tomorrow's videos, I'm going to cover these two. So I'm going to cover these two, and the video next week we will cover KNN and iterative, and I'm going to break down the complete mathematics of KNN and iterative. Their mathematics is very detailed, and if you understand it really well, you will be able to understand. Means think about when to use which particular algorithm, when to use which particular machine learning model. It's going to become easier for you to choose KNN in some situations just by understanding how KNN works. So when I will explain KNN imputer, KNN imputer is basically an application of KNN algorithm, which means the same way KNN machine learning model works, this KNN imputation is basically simply the application of that model. Okay, so iterative one is a very tricky one, and I'm going to explain the complete mathematics of it with examples. Okay, and I'm going to show you how to code it. So for today, I think that's it. If you guys have any question, please let me know. So let me see if you have any question. So before doing data cleaning, we will be using grid search CV for missing imputation. That's right, Lavanya. So I showed you how to do mean imputation, median, arbitrary, end of distribution, all of these separately. But you can see that it is an extra work I'm doing repeatedly or repetitively multiple times, almost kind of like the same stuff. Shouldn't there be a fast way to do it? The fast way is if we have this grid search CV, I can put in all the parameters. I can tell my grid search CV to take in these parameters, means check for median imputation, check for mean imputation, check for arbitrary or end of distribution imputation, see which one gives you best result. The one gives you best result, just stick with that. And it's going to be automatic, means you would just write 5 to 6 lines of code and it's going to do the job for you. Okay, and then always you were asking if the missing values are less than 5%, right? Yes, always. So you can see that in our data set the missing values were more than 5%, and you can see it changes the overall. So this blue one, if you look at this blue one, this was my original distribution. But here you can see the green one, which when I introduce the minimum value, it kind of like squeezed down my original distribution, given distribution of the data. And similarly with the red one, you can see it squeezed down further as well. When it is less than 5%, ideal, but if it is more than 5%, it will influence the distribution of the data. So over here, when I wrote that it does not disturb the distribution of the present data, this is conditional if data is less than 5% missing. So if it is more than 5% missing, then it's gonna change it. So it's gonna change it. So this thing only happens if it is less than 5%. So only then we can consider these imputation techniques that we studied so far. Absolutely, always that is absolutely right. So far all these techniques that we are using is if it is less than 5%. But when I talk about this random one, you would see that if I use this random one, most probably it will not change my distribution as much, my variance as much, my covariance as much, my correlation as much. So which means even if I have more data missing, I can go with this. So out of all the univariate one, this would be the best one, and I am saving the best one for the last. Okay, so because if I just do this one, then you would be saying that why exactly we are studying these? Because you should know these, because if data is missing less than 5%, then why bother doing some hard stuff? Just do this easy stuff and you are done. But these techniques usually are used when data is missing more than 5% of the data. So these techniques would be handy, multivariate ones. Univariate are usually handy when it is less than 5% missing. But if it is more than 5% missing, I would trust multivariate imputation more than univariate. Okay. Yes, Francesca, don't worry. Even if you're late, this will be uploaded on YouTube, so don't worry about it. You can watch it later. And So, Lavanya, how do we know where to use it? Just look at the amount of missingness. I have been telling you all the things that when to use. For example, if you see, I told you this is the condition. These are the best conditions in which you should use it. So first of all, look at the missingness of the data. Is it completely at random? If it is completely at random and less than 5%, use that. Similarly, we talked with mean and median imputation. Over here, the first thing I talked about is this thing, less than 5% missing, and for mean and median as well, the missing completely at random as well. Okay, and the same thing with the uh, complete case analysis. So when I talked about complete case analysis, I told you the first thing I told you was the assumption. The data should be missing completely at random and small amount of missing value, that means less than 5%. So which means you have to take care of these things. First of all, take a look at how much data is missing. And even if you ignore this mechanism, but if you know this mechanism, it would be pretty handy because it will be very handy during the interviews, I'm telling you. So if you know what you are talking about, for example, like whether the data is missing completely at random and you know the differences of them in real life scenarios, this does matter because you need to have very good, you can say, you should be expert in the field. For example, like domain expertise is where these things, how to determine whether it is completely at random or not at random, that's where domain expertise comes in. So if anybody has a domain expertise, they can determine, oh, whether this data is missing. Does it make it look like as it is completely randomly missing, or are there any biases involved? For example, like only a particular person who is missing every single time, or everyone is missing randomly. For example, like if there is a librarian, if you go to library and for example, like you look at the records of the book, that how many books were returned and everything. So on average, if 5% of the books or the 5% of the records are missing, and those records are not specific to any person, that means that data is missing completely at random. But what if that 5% records are missing and they are related to a person, some person, maybe Alan? If that is the case, that means it is not completely at random. It is due to it is specifically to that particular person. So it is related to something else. So that is missing at random. And then when I say missing not at random, which means someone is intentionally keeping it out or something like that, then that is not at random or something like that. So that would be a good example. So you always look at these things first and then determine. So that is the reason why when I'm coding and everything, I show you the missingness first. So for example, how much missing data is here. So you can see over here, we figured out the missingness. We figured out the missingness. And that's how I determine, oh, which one should I use and which one should I not use. Sounds good? So if you guys have any more questions, feel free to ask. If not, then I'm going to finish off this session for today. So if you have answered this, I found data that is missing not at random and is less than 5%. What should I use? So when it is not at random and missing, so I will cover that. So the multivariate techniques are where these things are going to come in, because since it is not at random and everything, domain expertise also comes in. And then in that particular scenario, if I don't have domain expertise, I would trust multivariate techniques. So I will not go with univariate techniques because sometimes the data is missing, and if it is not at random, then it would be dependent on neighboring features. And if it is dependent on neighboring features, multivariate techniques, the KNN imputer and iterative imputer, they work really, really well in those scenarios. So because when I say not at random, which means it would be due to some other factor. If it is due to some other factor, that means that factor would be in the neighbors. And if it is in the neighboring thing, then multivariate techniques like KNN imputer, iterative techniques would be really handy. So when it is not at random, I would go by that. Sounds good? Yep, don't worry about it. We will cover that in detail. So that would be separate. So I will make a one complete video for KNN and one complete video for iterative because their mathematics is a bit lengthy, but it is easy. So don't. So let me tell you one thing. If you want to excel in this data field, never be afraid of mathematics, statistics. So I'm offering you here a complete breakdown. So I will break down the mathematics. Ask me as many questions as you have and clear out any confusions you have. And here nobody is judging you. So ask me any question. No question is a stupid question or silly question. All questions are entertained here. I will entertain every question. Ask me and clear out your mistakes and understand the mathematics. And I'm telling you, if you understand the mathematics, you're gonna excel in this field really well. So you will kind of like beat 90% of the or 95% of the people out there because a lot of people are scared of mathematics, scared of statistics and probability concepts. Because if you understand them really well, you will see that data science is literally a science. Okay. Thank you so much, everyone, for joining in. And I will see all of you on Friday's session, which will be about, I will talk about automatic imputation technique, automatically select which would be the best technique, and random imputation. So have a good one. And if you have any questions, please write down in the comments. If you haven't liked the video, please like the video. And if you haven't subscribed to the channel, please subscribe to the channel. And please spread the word in your community. I would really appreciate it. Thank you so much.